So we will be continuing with the problem regarding the design of beam ISLB 350 that we have selected. Okay, so let us start. Now, I have told you that we have to now do the check for shear, moment, and deflection. So, um, you see, for shear, if we draw the beam, the load was 60.73. So if this is W and this is L, the shear force will be WL by 2. So if we calculate it, we get this one, 151.83 kilo Newton. Okay, now this is the applied force. So we need to now find out the capacity. So capacity in shear, okay, should be greater than applied force. Okay, so the formula for the capacity in shear, which is equal to Fy H Tw by gamma m naught root 3. Okay, so Fy is 250, then H is 350, total depth of the section, Tw is 7.4. Okay, then gamma m naught is 1.1 into root 3, and we divide it by 1000 to keep it in kilonewton. So ultimately what we are getting 340 kilonewton, which is greater than the applied value of 151.83 kilonewton. So we can say that it is safe. Okay, now we should also see that, like, we know that Vd is greater than V. Okay, the capacity is greater than the applied force. Now, only this will not be sufficient. We should also see that even zero point 0.6 of Vd should be greater than V. Okay, that means 60% of the capacity should also be greater than the applied force. So, what is the 60% of Vd? It is 0.6 of Vd is 340. Okay, and we see that it is greater than 151.83. Okay, so this is fine. Okay, this is fine. Otherwise, if we would have got that this 0.6 Vd is less than V, then this was a condition of high shear. So this is no longer valid here. Okay, we already have got that even 60% of our capacity is more than the applied force, so it is fine, it is okay. All right, so let us proceed. After this, there is one more thing that you need to know, which you will get from clause 8.4.2.1. Okay, this d by tw. Okay, if see in web, okay, either we use stiffeners. Okay, either we use it or we don't use it. Okay, stiffeners are used to what? Increase the stability. Okay, these are additional elements which are added to the web to increase the stability, but in our case we don't have stiffeners, right? We don't have stiffeners. So if we don't have stiffeners, then we have to check this d by tw, okay, with this 67 epsilon. This epsilon is again this root 250 by fy, okay, which is equal to 1. So this is 67. Now our d by tw, which is the value that we have got, which it is now less than 67 epsilon. Okay, you can check the value that you have got, it is 39.9. Okay, so this is less than 67 epsilon. So then what we can say that the web is strong against shear buckling. Okay, the web is strong against shear buckling. Now let us go to page number 53 of the IS code. Okay, so when you go to page number 53, you will see clause 8.2.1.2 where which you will be using for the check for moment. Okay, so the formula for the design moment given is md equal to b zp m naught. Okay, now our one is a plastic section, so beta b is 1. Okay, now zp is what? It's the section modulus of the section that we have considered, which is 851.11 into 10 cube. Okay, then fy is 250. This is cube, and this is 1.1. Okay, so when we put all these values and we convert it into kilonewton meter, okay, we use these values and we convert it into kilonewton meter, we get that the value is 193.43 kilonewton meter. Okay, now this 193.43 kilonewton meter is the capacity. Okay, 193.43 kilonewton meter is the capacity, and this should also be checked against, okay, one term which is called as 1.2 ZD Fy by gamma m naught. That means this 193.43 should be less. Okay, should be less than the value, or equal also, it is fine. Okay, so we have to do this additional check also. So let us do it. Elastic section modulus ZD, okay, for ISLB 350, Okay, you will get it from the IS code. Okay, is 751.9 into 10 cube. Okay, mm cube into 250 divided by 1.1, and you keep it in kilonewton. Overall, this value in the right hand side, you keep it in kilonewton meter. So you will get ultimately 193.43 is less than 205 kilonewton meter. Okay, so ultimately this is satisfied. Okay, so we have satisfied our condition. Okay, and this 193.43 is 193.43 is also greater than the applied value of 190 kilonewton meter. Okay, applied moment. This is the applied moment. Okay, now we check for deflection. Check for deflection. So if we consider a simply supported beam, okay, having a span L with a UDL W, the deflection is 5WL4 by 384 EI, and this W, okay, is the live load, okay, and it is the unfactored, okay, unfactored. That means in case of W, you have to write the unfactored live load. Okay, so that you should always remember. So if we now try to solve it, what we will get? Deflection is equal to 5 into what is the unfactored live load? It is 20. L4 is 5 to the power 4. Okay, so let us keep it in like you can say 1000. Okay, in mm. Okay, then 384 EI, 384 EI. Okay, so now 20 kilonewton per meter. This 20 kilonewton per meter, if we convert 20, then it's 1000 Newton by 1000 mm. Okay, so ultimately 20 Newton per mm only. So that's why we have written here mm. Okay, here this 20 will be Newton per mm. Then E is what? For steel, it is 2 into 10 to the power 5 Newton per mm square. And I will be, okay, you will get it from the steel table. It is 13200 into 10 to the power 4 mm 4. Okay, and this will be IZZ. Okay, IZZ, it is 13200 into 10 to the power 4. So ultimately, when you do the calculation, what you will get is delta equal to 6.165 mm. Okay, after doing the calculation, you will get delta is equal to 6.165 mm. One one thing that I want to tell you is, okay, sometimes you may see some variation, okay, in the values that you are considering, okay, like uh, in in this step, the value that I have told you for IZZ, okay, it might not match with the value in your steel table. Okay, it depends on the edition that you are using. Okay, it depends on like which edition, whether you are using a old edition of a steel table or a new edition of a steel table, or which author you are using. Sometimes like the values gets changed. Okay, so like I follow like the book for Subramanian. Okay, book by Subramanian. Mania. Okay, this is like one of the best books. Okay, preferably the best textbook for civil for design of steel. So the values in the problems for Subramaniam may differ a little bit from the steel table. Okay, because like when he was writing the problems and all, he might have used the steel table of some other version and all. Okay, so don't worry, don't get confused. Okay, by looking at the problems, and some if you see the variations, don't get confused because it depends on which version you are using. Okay, you should always be sticking to one like updated version. Okay, so now I am solving one problem from Subramanian. So the value that he has used is 13200 into 10 to the power 4 mm4. Okay, and you may see that in your steel table it is different, so don't worry about it. It depends on like which year he wrote the problem and all. Okay, so all these things matter. Now this delta that I have got, 6.165 mm, should be less than the allowable maximum deflection. Okay, so allowable maximum deflection, for that you need to go to table 6, page 31. Okay, so here we will see that we are looking for live load. You go at the bottom of the table, live load, and floor and roof you have to select because it is lateral restrained. Okay, the floor and roof criteria is selected because the beam is laterally restrained. Our beam is like this, isn't it? This was our beam, and suppose if you give a support, very heavy support, okay, at the top of the flange, okay, it can be in the form of a slab, okay, which may be due to like the floor or roof. Okay, so when there is a slab, then it cannot move sideways like this. Okay, this is not possible. So that is the concept of lateral restraint. Okay, so this beam, okay, that we will be considering will be for floor and roof. Okay, now uh, here again there are options for like floor and roof. Floor and roof, there are options. One is members susceptible to cracking and elements not susceptible to cracking. Okay, so one is elements susceptible to cracking and another is not. This you can decide with due to the help of from the help of d by tw. Okay, so it was less than 67 epsilon. Okay, so if generally you get this condition, you can say that the web, okay, this is for the web, okay, this web cannot be affected, or like there is a very low chance that it will be affected by the shear. Okay, so there will be no cracking and all. Okay, so this cracking will not be happening. Okay, there is a very high chance that the cracking will not be happening, so you have to select this. But if sometimes you get that d by tw is greater than 67 epsilon, that means the web may be vulnerable to cracking. Okay, so that luckily this is not the situation here. So we will be considering elements not susceptible to cracking. Okay, so our web is not vulnerable to cracking. So for not susceptible to cracking, the permissible deflection is L by 300. So L by 300 will be how much? So this is the maximum permissible deflection, okay, for elements not susceptible to cracking, which you have got using d by tw less than 67 epsilon. If this would have been greater, once again I am repeating, if d by tw would have been greater than 67 epsilon, then it would have been susceptible. Okay, but this is less, so it is not susceptible. So what we are getting is that the deflection 6.165 is less than 16.67. Okay, so it is safe. So this is the end of the problem. Okay, thank you.